Hey everyone, welcome to my video on the center of mass for 2D laminas. This is part 2. So in the last video I should have seen going through something like this where we looked at a shape between two curves and kind of dividing it into these small thin rectangular pieces, and then using the ideas from before with the center of mass on composite shapes, where I'm basically just finding the mass times distance based on a 2D point mass with the center right there in the middle of the rectangle and the mass of that rectangle kind of proportional to the area. So just using the area as that, and then adding them all up to get the moments and the masses, and then dividing those out to get the centroid. So all this chart should have been filled in through the last video, and you can go ahead and go through those ideas again if you haven't already. Just take a look at that first. We're going to kind of summarize these guys right here. So the definitions we ended up at the end of the last one were the mass is basically the area, so this integral of f minus g, if we assume f is on top, g is on bottom, f minus g times dx, that's the area of the rectangle. And the actual mass would have like a density function, but we're just going to assume density 1. For the centroid, once you divide these moments and masses out, then those densities divide out anyway, so we'll just assume 1 for these guys. The moment about the y-axis, again, assuming density 1 is just going to be that distance x times, again, that kind of area that we're looking at, so that f minus g times dx. So that's the mass times distance from the y-axis, which is x. And then the mx, if you're looking at just strict mass times distance, we get this area mass right here, and then the distance going up is just an average of the f plus g. So f plus g, take the average, that'll get you right in the middle of the two. This will also simplify to what you see in a lot of textbooks as this formula right here, using that difference of squares. So this will simplify to f squared minus g squared. It is important that you do not write it as f minus g quantity squared. That is different. So just leave it as the two differences squares right here. Those two separate pieces. Do not put the square on the outside. Alright, so we're going to go through some examples in this video, and but the main one I wanted to start with was this just basic sine and line right here. So trying to, and you should have your own lamina shape in your kit, so it should be kind of an orange piece like this that you can take a look at. So what we're going to do here is go ahead and define these functions, our f and our g, and again we'll use top one is f, bottom one is g, and go through some of the calculations, and then you can check at the end by balancing that shape on your fulcrum stand. Make sure you got the right spot. So f, we're looking at a sine curve, and you might have to do a little bit of refreshing on how to come up with the equations of these curves. But if you have a sine curve, right, it looks like amplitude is 1, so no change in amplitude. It does look like there's no shift left or right, starts right on that midline. No shift up or down, but you do have a period change, right? A period of 4 instead of 2 pi. So remember, you can always do something like this. Period is 2 pi over k, where k is the number in front of your x, basically inside the sine function, or you can swap these. K is 2 pi over the period if you just rearrange the equation. So we'll go ahead and use this period of 4 right here. Find that k. So 2 pi over 4. That'll simplify to pi over 2, and we can go ahead and write that right in here. So we got the sine of pi over 2 times x. Alright. The g of x, we just got a line, looks like a slope, negative 1/2, and starts at a y-intercept of negative 2, so we'll just get this negative 1/2 x minus 2. Alright. And we're on the intervals 0 to 4. So these will be our bounds in our integral, so 0 to 4. And then go ahead and calculate these guys out. So we're looking at my. This again is from the y-axis, so you can go back to your definitions up here. So this is going to be x times this f minus g. So we would get this integral from 0 to 4 of 0 to 4 of x times f minus g. So this would be sine of pi over 2x minus this negative 1/2 x minus 2. And you could go ahead and distribute and kind of simplify that if you wanted. With our dx right there. So I'm going to go through and calculate these depending on the order you go in the class. You may or may not be able to figure out this integral. So if you distribute the x times these will just be power functions, and you can do those pretty easily. But the x times that sign, if you haven't done integration by parts yet, you're not going to be able to figure that one out. There's really no other way to go about doing that guy. So if you haven't done integration by parts, there's several integration techniques usually in a chapter that you'll go through, and sometimes people do those before the application, sometimes they do them after, so it just depends on your class. If you haven't done that, you won't be able to do this one by hand. So we're going to go ahead and just save some time anyway, put this into Desmosen to get an approximation out of this guy. We'll do that there in a second. Same thing on this one. Here we got integral 0 to 4, and we're basically going to do f squared minus g squared. Don't forget the half on that guy in front. So we're going to get this sine squared pi over 2x minus, and then this whole, again, included in parentheses, negative 1/2 x minus 2 quantity squared. You don't want to distribute the negative on that. The squaring is going to take care of a lot of that there, but you do want to make sure that 1/2 is either outside the integral or outside the parentheses right there. And the actual way I'm going to do these, here in a second. I got integral 4. This will just be my f minus g. Sine pi over 2x minus that 1/2 x minus 2. Negative 1/2. So I'm going to switch over to Desmosen and go ahead and calculate those out. And the way I'm going to do them is to just input my function. Alright, so f of x is sine of pi over 2, that way, times x. I'm going to do g of x is negative 1/2 x minus 2. And if you really want to restrict the range, this isn't strictly necessary, but you can put these in brackets and restrict that to just the part you're looking at. So again, you don't have to do this part, but say 0 to 4, make sure, and you just type less than and then hit the equal sign. There's no magic button for that, you just do the 2 separate keys. And that'll give you your bounds that are right there for that function. And then go ahead and put in my integrals. So integral 0 to 4 of, let's do the area, actually we'll do it in the same order. So we had x times, and we can actually just do f minus g. You have to put the of x's on here. So x g of x and that'll calculate that out. Since it's a bounded integral, it's just using the numerical approximations on that. This one, integral 0 to 4 of 1/2 times, and again, you put that 1/2 outside the integral if you like, but we'll do f of x squared, and then minus that g of x also squared. Alright, and then the last one here, which is just the area. So integral 0 to 4 of this f of x minus g of x. Yep. And we like parentheses around these usually, so let's put those in. And then we can go ahead and divide these out. So we're going to have for our x bar this 24 divided by 12. So if you just want to be that 12, you can do that. And let's go ahead and plot this as a point. And then for the y, we'll have this mx, so this negative 17. Makes it repeating. Also divided by 12, and that'll give us our point right there. If you want to get the decimals for those, I guess we'll go ahead and copy those here. So 2.01 about for that one, and about negative 1.472 for that y coordinate right there. So that's just a quick rundown going through. The main thing we're looking at is kind of the setup, and then again, if you've done integration by parts, you might be able to do this by hand, and your teacher may want you to. But if you haven't, then you certainly will get stuck at that integral right there. But the setup is the main thing that we're looking at on this one. Alright, so I filled in all the information on the worksheet and put down just all the values that we found in Desmos right there, and then you can go ahead and plot that. And again, you should have a lamina shape that you can actually put on the stand and see if that is balancing on that point that you marked. So let's use your dry erase marker. You can put it on the grid. I believe these should be the wide grid, not the skinny grid ones. So go ahead and try that and see what you get. There are several more problems in this worksheet, so I'm going to say try several of these. And again, you won't have maybe a physical shape for this one, but you should have for this one. It's a parabola, so I kind of give you a hint in the title. It's a parabola and a sine curve. This one obviously lines with this extra box shape right here. So this you would want to actually find, use your composite idea. So find, say, this line down to the x-axis right here, and treat this as like two triangles and then this rectangle that you can do a composite type of idea. And then this last one, it's a parabola, and then this bottom one is a square root function. So it's been flipped upside down and kind of stretched or compressed with that one. So, but that is a square root function on the bottom. And then again, there's a hole taken out of it, so you're going to need some composite ideas with this one. We'll go through this number 5 in a separate video, but go ahead and try it, see where you get stuck, where you're having trouble, that sort of thing, and then you can check out that other video for this one. Homework at the end, as usual, even some OpenStax problems, but that'll do it for this video. I just wanted to show you a main example, and then, like I said, we'll do a composite one in the next video.